And then if I make this full screen. All right. So as I stated earlier, we looked at a number of, we've looked. And then if I make this full screen. All right, but a number of finite elements, and today we are going to look at, as I stated earlier, we looked at a number of, we've looked. And then if I make this full screen. All right, but a number of finite elements, and today we are going to look at, as I stated earlier, we looked at a number of, we've looked. Sorry for that. It seems that we have an issue with the audio from my end. I'm looking at my microphone, but in a short while, we are going to be back, and I'll start again from the start. Okay, let me take back my slides where we are starting so that no one is left behind. So thank you for those who have commented on the audio. I think there was an issue. I had shared without sharing the sound. So let me just do the retake again. Then we shall see. And then if I make this full screen. All right. So so let me just do the retake again. Then we shall. I believe the fourth type. This is a plane frame element. And if you can remember from what you've been studying, we have what? Let me arrange my desk here. Okay. We have, consider a portoframe, something like this. Or even, let's make it more interesting and have it slanted portoframe like that. Okay, I know you have analyzed sway frames. Okay. So whereby we had the application of load here. That mouse pad is not very good. And then you did the sway analysis in that case, and you could talk of the typical deformation mode being something like this. Okay, I know you know this kind of stuff. So we are going to do or to conduct the same type of, or we are doing this analysis, but of the frame, but now with the finite element approach. And in this case, for the frame, remember for the truss, we assume that these are pin joint. Okay, but now for the frame, these are rigid joints. So when they are pinned joint, it means there are no movement that you develop because we have around rotation. It's not fixed. Yeah, but when it's fixed, when the joint is rigid, it's fixed, then it means moment will develop in these edges. There will be moment developing. So if you take like a typical row-rise structure, maybe a factory setup where we have the wheel loading kind of, so we may have a UDL here, and then it's a portoframe, maybe of concrete or steel frame. Okay, so it means in this, if we can take this just this element here, we can consider just this element. Okay, you can see this element 1, this as the slanted one is 2, the other one is 3, and another one is 4, right? So that being said, once we discretize, let's say this node 1, this is node 2, this is node 3, this is node 4, and node 5. So if we can take an element 2, typical, that is slanted like that. Okay, it's oriented from the horizontal. You see the angles are measured from the horizontal x direction, counterclockwise. So this angle, you can call it theta, or some books they say phi, right? So we want to consider now this. If it was a beam, we would consider only the vertical load because the axial loading is neglected. But now for a frame element, the issue now of axial loading comes into play. Okay, so for the bar element, we said for the bar, we consider, because of the pin jointed, we consider axial loading. For the beam element, remember during the analysis, we just considered the beam oriented in the, the local coordinate system coincided the global coordinate system, and we just considered beams which are oriented in the horizontal x direction. So in this case, we did not talk about the transformation because when we come to the frame, the analysis that we are going to do is like we are extending the beam oriented in an arbitrary angle or arbitrary plane from the horizontal x direction. And again, now for the beam, because we neglected the axial effect, now for the frame element, due to this rigidity here, if a load is applied there, there will be axial transformation, or axial loads will be transmitted, and also as well as the moment will develop, as well as the vertical or the transverse loading. So for the plane frame element, we combine the truss element and the beam element. We combine the axial load and its corresponding effect. Axial load brought about the translation, okay, the deformation. And once it's oriented in a certain plane, when it's not on horizontal, it's oriented. Now we consider also the vertical displacement and the horizontal displacement. And now when we consider the beam, we bring the issue of rotation and the moment, right? Good. So let's consider this element too. This is the element I've extracted here. And now this is what I'm starting off with here, okay? So this is the plane element. Plane meaning we are just considering it in 2D Cartesian plane. Okay, we are not considering the depth. So it's not a space frame, it's a plane frame. Okay. So this is a portal frame like that. Okay. And we have extracted this element. So this is the element here. And this plane frame element, so we are saying if it was just a truss or a bar element, we'll be considering the axial loading. So we'll be considering this and this. But now, because of the rigidity, we say now the beam effects, the moment you develop. So we also introduce now the moment here. Okay. So as I'm saying that it's just what we have done and then we are combining, but now you should also be aware that the complexity of the matrices, the degree of complexity increases. Because now you see we are combining bar and beam. So the number of degree of freedom at any one node increases. For the bar element, it was 1 degree of freedom. Bar element in 1D bar elements. Now, when we talk of when it's inclined in 2D space or 2D plane, then it became 2D. Now, for the beam elements, we talked of typical at the elemental scale, elemental coordinate system, 2 degrees of freedom. That is rotation and vertical displacement. Now, for the plane frame element, now we have the 3rd degree of freedom. All right, and now that is considering if we take it as elemental scale and element scale at local coordinate system. Okay, remember the issue of now global coordinate when we have oriented it in space. Now the issue of the other axis makes our matrix expand. So, but at one node, we have vertical displacement, horizontal displacement, and rotation, and the corresponding nodal force or nodal loading vector will have the vertical shear force or vertical axial load, vertical transverse load, the horizontal or the axial loading, and then the moment. The moment is brought about by the rotation. Vertical displacement, then we have the shear force in the y direction. Then horizontal displacement, we have the axial force. Okay, so you have to see F is equals to KD, because that's our governing equation. F is equals to KD. The force vector, in the force vector, the force component must correspond with the displacement component. Yeah, that's why we are saying moment correspond to rotation, because we know rotation towards the z-axis is towards the plane of this paper or your screen. So rotating about that axis, that rotation is one that brings about the moment. All right. So that being said, so as you can see in this sketch, we have shown the different axes, and now here I'm using a different reference book. So the coordinate, the naming of the coordinates is different, but it's just a matter of notations. So initially, the other examples we are writing capital Y and capital X to represent the global coordinate system. And then we are representing the local coordinate system by applying. But in this case, the global coordinate system is denoted by a Y naught. There is a raised to power naught, something like a degree. So Y naught. So this is a global coordinate system, So this is a global. Then the other one, which are not indicated with anything, then they are denoted by any marker or mark, then that is the local coordinate system. Then with that, we have shown the moment, we have shown the axial displacement and the vertical component. So let's see. So for this one, for the derivation of this equation is nothing much but just combining the bar and the beam. So stiffness matrix. So you're saying we are moving from the beam in the horizontal axis. Initially, we had a beam. And for the beam, remember the equation, the EI over L cubed into brackets. Remember the 12, 6L, 6L, 4L, 4L squared, like that. You continue finalizing that way. So we are transforming from the beam to the frame by orienting the beam in an arbitrary plane. So we are moving from this. So what happens when we are transforming, or when you are translating our beam, or transforming our beam from the horizontal or the local coordinate system to the global to make it a frame? So this is a beam oriented maybe in that direction initially. And then for it to be a frame, we orient like that, and then we introduce the issue of the axial load. Okay, so what will happen is that this is the beam equation, this one, and then we had the VI, theta I. We ignored or we neglected the UI, the axial effect. So in the frame, we bring in the issue of the axial effect, and the axial effect. Remember the UI, VI. UJ, VJ that we talked of in the bar element. That's when we have the EA. We had the EA over L issue. So we are going now to bring in. It's like this. This is the beam element. We combine with the truss, the beam element stiffness matrix. We combine with the truss element stiffness matrix. Yeah, the EA over L minus EA over L. Okay, like that. And then we put it in the same matrix. So we are going to introduce a new row and a column associated with the axial effect, the UI. So you're going to have the UI here, and then UJ. The same case, we are going to introduce a row for UI and UI, UJ, VI, VJ. Okay. Let's see what I'm saying here. This is what we are saying. We have introduced a new component here, not new per se, but now we have brought in the issue of the axial effect, the UI and the UJ. For the beam element, you only considered the transverse displacement, okay? The VI and the VI, VJ. So EA of L, I know you know this, EA of L minus EA of L, E minus E of L, E of L is the stiffness matrix for the bar or the truss element. So what we are saying is that you augment your matrix. You use the word, we mentioned about augmenting, you expand your matrix. And then, of course, because we know there is no correlation or there is no relation where the node UI and VI are related, you put zeros there. Okay, so these are zeros. So if you look carefully, you can be able to extract what belongs to the truss and what belongs to the beam. So this is so simple. And this is the stiffness matrix for the plane frame in the local coordinate system. So local coordinate system, that means for any, even if we are talking of this kind of a frame, okay, where this element, where element 1 is oriented in different direction from element 2 and element 3 and 4 like that. So we are saying all of them in local coordinate system, we can use this equation to get the stiffness matrix. Yeah, so you just need to plug in the figures. But then before we think of plugging in the figures and getting what is K, we need to understand that the procedure for analysis of finite element analysis, that once elemental stiffness matrix, we need to get to assembly stage to get the global stiffness matrix. And the global stiffness matrix, we cannot combine different elements which are oriented in different direction. So we need to bring them to the global coordinate system. That's why we need to do the transformation. Now, in transformation, we have the transformation matrix that we derived for the bar element. And we said a broad statement, which was the catch or the catchphrase or the what was being checked in the previous assessment. Where, for those who have been able to view that, where the spring element, although initially when we started the spring element, we were at the introductory stage, so we did not introduce the aspect of transforming. So we just considered the spring when they are oriented in the same coordinate system. But then we said any coordinate in the local coordinate system can be transformed. Any element, any component, whether be it displacement, be it the boundary condition, be it the loading, in local coordinate system can be transformed to global coordinate system utilizing the transformation matrix. So the transformation matrix is kind of a standard for transforming a local coordinate component to global coordinate component. So this is the same transformation matrix that we are going to utilize to transform this to the global coordinate system. And to do that, we are saying, now this one we are simplifying so that we can be able to understand. So we are saying for this notation that we are using here, it doesn't mean that you cannot use the notation that you're using previously, only that I didn't want to change so much with the reference book that I'm using now for this example. And where we have this is the local coordinate system, so you could talk of the U plane, if you're talking of this of the displacement, to be equals to the transformation matrix times the U in the global coordinate system. So same case for the forces for the any component. Now here we are using this component, so we are saying from local coordinate system to global coordinate system using the transformation matrix. And now we have simplified. Remember here we had 0, 0, 0, 0. So this is what we are calling of, we are writing 0. Remember a matrix like this, you talk of a matrix of a certain order, okay? If the matrix is made of number 0 or the element 0 or the member 0 and it's of 2 by 2, you talk of order 2. So you just write 0. Okay, this is what we are simplifying to avoid writing so much, because already by now you have come into understanding of the nature of this transformation matrix. So what we need to do, remember here we are just considered UI, VI, UJ, VJ. This was associated with the X coordinate and the Y coordinate. But now we have brought about the issue of the rotation. We have brought about the theta. Theta I, theta J, okay, which will be associated with M1, M2. This one will be inserted here, right? And bearing that in mind, it means we need to augment or to expand our transformation matrix to incorporate the effect of rotation, which will bring about brought about by the moment we develop. And then one thing we know is that the rotation is towards the plane of the paper. So in as much as the element, if you can consider your bar, your plane frame, like this, so we are talking of the component. So we are talking of the displacement in that direction and the displacement in that direction. They need to be transformed to comply or to be like the way we did resolution. Consider the way resolution of the joint. We are resolving on the x and y direction. But for the rotation, it's neither in the x, it's neither in the about the x or y direction. It's about the z direction. And the z direction is not changing, right? So we introduce theta here, but in our transformation matrix, that's why we'll have 0, 0, 0, 0, and the transformation for that remaining 1. So the component for theta remains. I mean, we do not need to resolve it to x and y because it's not related to those axes. Okay, and doing that, that's why we have this kind of matrix like this. This is a transformation matrix. This is a transformation matrix for the print frame, incorporating now all the axial effects, all the displacement effect or component. So the axial effect, this is the U, I, the transverse effect, UI, and the rotation effect, theta I. Same case, UJ, VJ, theta J. So this is a transformation matrix, and this is the transformation equation from the local coordinate system to the global coordinate system by pre-multiplying the global coordinate element or component, pre-multiplied by the transformation matrix. So you can see the concepts are the same with what we covered in the previous lesson for the bar and the for the bar element and for the bar then truss. Good. Now let's see. We can write this, of course, in short form. So this slide is just a summary of what is written in short form. So you're saying from the local coordinate system to global coordinate system, you need to pre-multiply by the transformation matrix. The transformation matrix can be written in a condensed form. This is zeta. This symbol is Greek letter, zeta. So where zeta is this direction cosine. Cosine minus sine cos 0, 0, 1, 0, 0, 1, like that. And then you also need to recall that we said now to transform our stiffness matrix from the local to global coordinate system is T transpose, or the transform matrix, the transpose of that, times the K in the local coordinate system times the transformation matrix. And we said the order is very important. Again, what we just need to note that for the frame element, we are talking of the transformation matrix, the stiffness matrix for the rod or the bar, you combine with that of the beam. That is K, note, is K rod plus, or K bar plus K beam. So that's simple. Where K for the rod, you see once you introduce the theta, of course, this is just augmented matrices for the bar element, A over L, or E over L, but where you have the theta for the bar, the whole component here is 0. The elements are 0. So you have the cos squared, cosine like that. So if you look at the previous note on the bar element oriented into this space, we didn't have this part. So we're just introducing it because we know we combine the two, we need to augment the matrix to have all the components included, all the displacement component, all the degrees of freedom per node, which are 3. Now, for the beam elements, of course, you can work this out to see when you pre-multiply, when you multiply this, you know you are using this equation, KT transpose. So you take for the beam element, this is a transformation matrix, this one. This is the beam element, the beam in the, now if we do not have EA over L, of course, we need to augment. EA over L, this already we have combined. By the way, whatever we are saying, K rod plus K beam is equal to K frame. This is the K frame in the coordinate system. So you can just pre-multiply this. You can just pre-multiply this with you can just do this pre-multiplication this is the transformation matrix. You can just do this multiplication here. Pre-multiply by the transpose of the transformation matrix times the K, where K for the overall frame could be the one that now we have said is including the beam element and the frame, the truss or the bar element, and then you multiply by the transformation matrix. Or you could do them separately, like the way you are saying, you first argument, you include for the theta. So of course, for the beam element, the U component, again, will be considered, and then you pre-multiply, you do the multiplication, K transpose, T transpose times K prime times T, you're going to obtain this, right? For the rod or for the bar, we are using rod to differentiate between B and B, because if you said for the bar, you could say KB, KB, KB. So you're saying K rod or K truss. All right. So this one I'm saying in an exam setup, you should be able to direct this, but in an exam setup, you should be given this. And with this now, why this book or this reference was separating them is because it's not always necessary, or it's not always in all cases where the issue of the axial effect will be of consideration. If we have very rigid members in axial rigidity, stiffness is high, that we're not considering obligation, then it means this component may kind of disappear. But let's see with an example what this means. And we also see a case whereby we can combine or use the combination, we transform, or we use the stiffness matrix when we have incorporated all the components for the truss and for the beam directly. So those are the two different approaches that you can use. So this example, for example, it shows just a typical frame. And in this reference, they are saying, if you assume that the stiffness, the axial stiffness of each element is very large compared to the flexural stiffness, that's why now the effect of this part disappears. Okay. Therefore, the frame, the K for the frame will be the K for the beam oriented in arbitrary direction, which is this one. Okay. Now, let's see the solution for this. Before now, I can welcome some questions. I said today is simple, is very easy. It's an easy task. But the workout, the computation now start becoming quite a task, because the matrices start becoming quite large. Okay, and this is why the computation power of the computers now come into play. All right. Now, looking at this, it's a simple frame, and you're given the length, the dimension, and the load is applied at node 3. And then you are required to determine the nodal bending moment. Okay, the bending moment at the node. So this statement that it may be assumed that the axial stiffness of each element is very large compared to the flexural stiffness, that means we can be able to neglect the issue of KR. Okay, so we just use the equation, the stiffness matrix KP. So that's what it means. We are going to see a case whereby you don't need to disregard that, or you don't need to be worried about that statement. So that being said, now what we need to do now, go ahead the same way we are doing with the other examples. This is, let's call this element 1, this is element 2, element T, or as the book says, this one book, the reference book says, element 1, 2, element 2, 3, element 3, 4. So again, remember we said that God are measured at the lower node. So IJ, where I is the smaller node, the lower node, in terms of counting numbers. So if this is the element 2, 3, I will be 2, J will be 3. And then we measure the angle at this node, starting from node I, counterclockwise from the positive X direction. So this angle is 90. Okay, that's why alpha or theta is 90. Cos of 90 is 0, sine of 90 is 1. So these are direction cosines. The length is 3. Again, we have simplified matters here. for clarity of working, because our matrix is going to be bigger. So to reduce the working, because we knew one thing. When you come to the solution, we develop what you call the reduced stiffness matrix. The reduced, not stiffness matrix, the reduced finite element equation. And we reduce it by removing the rows and the columns associated with the degrees of freedom, which are equal to 0. So here, looking at this this frame, you just need to look at the displacement. I mean the fixity, head fixity. Okay. And the head fixity here, this is fixed support, this is fixed support. It means now you should be able to tell how this will deform. Let me also bring something else. We are saying the axial rigidity, the axial stiffness is very large. The axial stiffness is very large. If the axial stiffness is very large, it means the element will not erogate. Okay? Will not deform in the axial direction, element-wise, not the frame. The frame, of course, will sway, it can move up and down. So what we are saying is that these are very rigid, the axial stiffness. So the deformation here, if it's something like this, okay, so the length will remain the same, and then something like this. Because of this fixity, because of this fixity here, the angle rotation here is 0. The angle here is 0. And of course, the displacement, the U1 and V1, U4 and V4 is equal to 0. So for this element, and again, if there's no erogation, the axial stiffness, maybe, of course, maybe let me clarify this here. This could or could not, based on the flexural stiffness. But we know, one thing that we know is that this member will not erogate. So it's kind of moving as a rigid body, but it can deform. Okay. The flexural rigidity may be not very high, but the axial rigidity, but we are saying this length remains the same. So if this load applied here causes a sway, and there is a deflection of amount delta here, which delta we can call it U2, because it's the horizontal displacement at node 2 global for the structure, not for the member, for the structure. So the same value will be experienced here, because we are saying the element by itself does not stretch, okay, because of that axial rigidity being very high. So this deformation here, which is U3, is the same as this. So U2 is equal to U3. Okay, we are just interested, at this stage, we are interested in the first element only. We are just interested in this element 1, 2. So we have found that U1, V1, theta 1, as a matter of the fixity, is equals to 0, and V2 is equals to 0 as a result of the statement. Axial stiffness is very high. Axial stiffness is very large. It means no erogation. It's so stiff. The members are so stiff that even if they are pulled, they do not stretch. So it means the displacement here upward, V2 is equals to 0. Okay. Good. And therefore, these boundary conditions enable us to know that at the end of it, we'll be able to remove these rows and columns, U1, V1, theta 1, U2, U1, V1, theta 1, and V2. And that's why, to simplify our workings, we have assumed that this one will be removed later on. Okay. I'm doing this because we have already covered quite a lot in the previous workings, and therefore we can move comfortably. Remember, this is not theta, this is for this part. So we can move comfortably, removing those components, the one associated with the U1, V1, theta 1. We'll be left with U2 and theta 2. So even V2 here will be, the V2 is removed. Okay. So note that this should correspond with the theta 2 here, which is missing in my slide here. Should be rectified. The theta 2 should move up, but in your handout, you should move this one up. Okay. So we have seen the stiffness matrix for element 1, 2. Similarly, we can do the same for element 2, 3. Again, for this element, you just need to look at the orientation. So it's horizontal, x direction there, like that. So it's oriented the same direction. So theta is equals to 0 or alpha is equals to 0. Where now cos is 1 and sine is 0, length is 4. And again, we know that for this element, we say the U2, the ones associated with 0 displacement, we know V2 and V3, vertical displacement here is equals to 0. And that's why we only be left with the components which are non-zeros, which are U2, theta 2, then U3, and theta 3. So this simplifies your working, but you also need to be very careful. If you cannot be able to observe by observation, then it does no harm if you just compute and fill the whole matrix and then cancel or remove the rows later on. Okay. So moving quickly, because this is simple, it's a repetition. So the same case for the element 3, 4. Of course, now the angle is this angle. If you look at it keenly here, you're going to see that measured from the horizontal x direction at the row node, starting from the row node, which is 3, this is the angle 270, which is the same as -90. So even if you say this is 270, so if you obtain the cos and the sine, you're going to get cos is 0, sine is -1. Remember this is what I talked of the unit circle, just to remind you of the mathematics you did in undergraduate. So we are in this quadrant. So in this quadrant, that's why you see it's bordering the cos and the tangent. And that's why at the boundary, the cos is positive. Of course, it's 0. So whether it's positive or negative doesn't matter. But in sine in this quadrant, in this area is equal to negative. Okay. But even if you punch in your calculator, you should be able to get that negative value. So that being said, again, we know for this element 3, 4. So you remove the rows of the rows and the columns associated with the component with 0 displacement, which is V3, U4, and V4. This one you know directly, altimetry is equal to 0. And then V3, which is vertical. Remember, this is the global scale. So we said these members will not stretch upon. Okay. So this means this U. But remember, why U is not equal to 0 here is because there is the sway. There is the sway. Okay. It's not the member stretching, it's the structure deforming. But by the element, now, because the load is applied in this direction, we know that this member here, this member will not stretch, right? The rigidity, axial stiffness is quite large. That's why you can comfortably say that the V3 vertical displacement at this node is equals to 0. And of course, this one now, the component at the node 4, they are known now because of the fixity. Yeah. So if it was pinned, now you need to know how the deformation about the this you learned from the column, the Euler's backwarding, and we talked about the effective length of column. For example, if it was pinned, you know now the deformation starts in that case. But if this is fixed, then you know here there is no rotation like that. It starts at a certain point. Okay. So that's that. Quite simple, right? And now we have the stiffness matrix for the whole, all the elements. So we just need to go ahead and assemble. And the assembly, again, you can assemble the whole stiffness matrix. If you assemble the whole stiffness matrix, remember you have how many nodes? 1, 2, 3, 4. And each of the nodes have got 3 degrees of freedom. So 4 times 3, 12. you shall have a 12 by 12 matrix. So that's why we are playing it smart now, because we've experienced this. And we are removing the rows for the unknown. Because now when you come to assemble, we just need to assemble. We just need to assemble using the rows and the columns associated with the non-zero displacement component, which are the non-zero displacement component are the U2, U3, theta 2, theta 3, because we say this is a typical deformation. You can say something like that, or if it's so rigid, you can, that one can maybe straight. So we are saying there'll be the rotation on this node. There is this displacement on this node. There is the horizontal displacement and the rotation. So at node 3, so U2, theta 2, U3, and theta 3. So that's only what we need to combine: U2, theta 2, U3, theta 3. That's what is necessary for us to assemble to get the reduced stiffness matrix. I mean, the reduced finite element equation. Okay. So, doing so, we obtain this U2, theta 2, U3, theta 3. So you're going to get this as a stiffness. This is a stiffness matrix. This is a K for the reduced. When you have reduced our matrix, removed the rows and columns associated with 0 degrees, the 0 displacement component. And then once we introduce the associated displacement vector and associated load vector, okay, where this is U2 is associated with F2 in the X direction. Theta 2 is associated with moment M2. U3 is associated with F3 in the X direction. And theta 3 is associated with M3. And looking at our figure, the sketch that we had, we know, if I go backward, we know this F to the snow load applied on this node. So we know F2x is equals to 0, F3x is equals to 5 kilonewtons. And note the sign convention, positive x direction. And there is no applied moment here and no applied moment here. That's why in this matrix, in this equation, all the other values are 0, apart from F3x, which is 5 kilonewton. And now this one becomes very simple. You can go ahead and you simplify. I mean, you solve for the unknown values of U2, theta 2, U3, theta 3. Because now this is just you are going to, if for example you take the first row, you're going to have 0.44, of course ZI is there, U2 minus 0.667 U theta 2 is equals to 0. So that's a simultaneous equation in just two unknowns. So you can create using this, the first row and the second row. We'll have unknowns of U2 and theta 2, so you can be able to obtain what is the values of U2 and theta 2. So U2, U3 is now obtained, solving this equation matrix, and theta 3, U3 is obtained. What would happen? This is a question by Benjamin. Thank you for that question. What would happen to U2 if the external load was applied at either node 2 or 3, acting downwards? What would happen to U2? If there is a load applied here, if let's say there is a load applied, if there is a load applied where? Here, downwards, right? So if there's a load, and the statement, okay, physically what will happen if this, remember our structure is allowed to deform, okay? So our structure is allowed to deform. Our structure is allowed to deform. Okay. So if there is a displacement at that part, that's an interesting question, because it overrides our initial assumption. But if you apply a load, consider that you apply a load, and then we still assume that our member axial stiffness is so high such that that load will not do anything to it, then we can assume that the member will not deform. But the structure itself, it's collapsing, just the same way we are saying there is this way like that. So our structure will deform. I mean, the structure itself as a whole is being pushed downwards. So what will continue to happen is that it will increase, it will add to the structure deformation. So the structure maybe will deform further. But remember, the length of the member itself will not change if the stiffness, if our assumption still holds, the axial rigidity or the axial stiffness is still high, very high, then it means it will continue to deform the structure, but the member will not elongate. Okay. Okay, let me know whether that is clear from your head. All right, and then where was I before I was answering that question? We were here. Okay, we have already solved for that. So you see, we have been able to solve, but our question requires us to get the moment. It requires us to get the moment. So you have obtained what is the global displacement component, U2 note and U3 note. To get the moment at the nodes, now we need to, what was stage? I think it was stage 8, 8 or 7 of the finite element analysis stages, where now we need to, once we get the displacement components, the degrees of freedom, now we need to start recovery stage, where we start calculating now to obtain the derived quantities, the moment. So we went back and now we extracted element wise, and then we started calculating the elemental nodal quantities. Okay, to do this now, let me bring about some few things here. To do this, we need to determine the nodal moment. So it means we are going to extract element wise, and then we start calculating the quantities at the elemental level. Okay. Now, recall from our lesson, the lesson which was on this, I believe, was on springs. No, it was on trusses. On truss. So for this one, we derived, when we are talking of the transformation matrix for a single node, node I, we started by transforming that single node. Yeah, it was for a bar element oriented in a scale, where I was drawing and using the similar triangles and using geometry. We first transformed one node, and this is the equation we obtained. Okay, whereby we said for a single node, we can transform the component from local to global coordinate system using this transformation matrix. But now this transformation matrix was only for a single node. That's why we used the tilde up there, that symbol here, and it was as shown here. So that you can be able to extract for any component you want. Remember, to get the moment, take for example that bar there. Take, for example, that bar there, okay? And you have a case whereby you want to get the moment, all right? So the moment we are interested, remember now this, you consider it as a beam. This is 1, this is 2, okay? This is node 1, node 2. We said for the element, now that's when we circle. Element numbering. Node 1, node 2. So this one, so what we are saying is that for the beam, I want to take your mind now to move from the frame and bringing you to the beam. To the beam element, because now we want just going to calculate the moment, right? So in this case, we take, this is the node I, this is the VI at the local scale, if I put plane. So V1, this is the V2, because this element is oriented in this direction. This is the Y, this is the X plane, okay? Our bar or our beam element is oriented vertically. So that now, if you look at this V2 in the local coordinate system, and you relate with our frame, right? If you relate with our frame here, all right, this is the displacement component here for the frame, okay? So this displacement component here for the frame, which was, in this case for the frame was U2 global, is the same as, if we take this element and we consider this to be the V, because now this one becomes the vertical displacement at this node for this element. So U2 global is the same as V2 local. Digest that. This is the element which we have extracted from the frame, okay? And because of the principle of compatibility, that the nodes remain together. Therefore, the deformation at the node is the same as long as the element remains together. The elements remain connected. Then this means the node, the displacement component for the overall, for the structure, the horizontal component here is the same as the vertical displacement for this element here, considering that the element is oriented as shown in this sketch. And to get the stiffness, of course, the stiffness matrix for this element, you already obtained it. So we need to get, we obtained V2. We are using this equation here. And as you can see, the sine and the cos, the negative M and L, U2, V2, you replace that, you are going to get V2 is negative 8.707 EI. And of course, V1, theta 1, this one and this support is fixed. So these are 0. And theta 2, of course, is as given. Beta remains the same. Now, this V2, if I can go backward, you can see U2 was positive. U2 for the structure was positive, right? For the whole structure, and you said because of compatibility principle, the V2 for the at elemental scale will be, of course, the opposite value. So you can see, even using this formula or by observation, we could be able to obtain what is the V2 for the that element one. Now, for those of you who got interested with whatever I had prepared in the latest tutorial, which was the derivation of the stiffness matrix, we talked of how we came up with the slope diffraction equations. So as shown here, the slope diffraction equations. And this one should not really worry you, but it's good you look at that video. This one you can extract them from the stiffness matrix of the beam element, because now you have come to the local scale. So remember the stiffness matrix for the beam, okay? K minus K, sorry, not minus K. This is K equals to EI of L cubed. And then we have 12, 6L, L squared like that. So I don't want to write all of that. So, and this, of course, when you write the equation, so if you allow me to go just slightly backward, so that you can see this equation, what I'm saying. This, let me go way back to the beams, where we had the beams. Yeah, this was the expression for the beam. And for these, let me show you something. So the slope diffraction equation, this was the slope diffraction equations written in matrix form. So you can be able to extract, for example, for displacement, I mean for shear force, Fi, we can be able to extract this. It's just EI of L cubed, then this would be 12 Vi plus 6L theta I minus 12 Vj plus 6L theta j. So these were the slope diffraction equations. So from not slope diffraction, these are from slope diffraction equation. So you can be able to extract the formulas that you can use for the at the element scale, at the local coordinate scale. For the beam, you can be able to get the force, the shear force, and the moment. So what we need to calculate the nodal forces, our nodal moment, is to extract the equation for Mi and Mj. Remember, we have I, J. And for our case, what we are talking of, we have 1, 2. So we need to get what are the moment here, what are the moment here. And the moment here is M1, M2. So we need to extract this equation. So you see Mi is associated with this rho. And the Mj is associated with this rho. So you just multiply or open the bracket, these times this, these times this, these times this, and these times this. Right. Now, with that in mind, let's go back to our question at hand. Okay. So keep on referring to those previous notes because they are very helpful. And those concepts that you ran there. So we are solving this example. So we have reached a point where we've obtained, we were calculating these angles so that now we can be able to extract from the slope diffraction equation. We know we need to get what is V2, V1, theta 1, theta 2, and so on and so forth. So once you extract the slope diffraction and use the equation for the moment, you can be able to get M12 is M1, M21 is M at node 2. So you just need to substitute the values of theta 1, theta 2, M1 and M2. Okay. So for example, for 1, 2, we are using, or we are utilizing this expression, whereby looking at this, we can be able to express or to simplify our expression, because this by itself, we know this is M1 6 EI over L square. L square, this is 9. So this is this part. 6 EI over L squared. Then we know V2 is minus. So you see, if we take this minus out, this one becomes positive. So V2 is minus 8.707 EI. V1 is equals to 0. So this part is this part here. And then this other part here. Okay, EI of L, okay, times 4 theta 1. We know theta 1 is equals to 0, so this disappears. That's why you have 2 theta 2 times EI of L. So 2, so this would be L is 3, so this 2 over 3, EI theta 2, which is 2.049 over EI. You get the moment to be like that. So the same case, you can use this expression to get for M2 or M21. And therefore, in a similar manner, you can obtain for the other element. We have obtained for one element. We have obtained for the final, I mean, the moment for this element. You can go ahead, extract that element, noting that that one will be, of course, now this coordinate system coincides with the global. When we come to this element here, you extract it there. So you see this will be the direction Y, and this will be direction X, because this is node I, 3, 4 here. Okay. This is node 3, this is node 4. So this is X, this is Y at local coordinate system. So you do the same that we did with this element, and you'll be able to obtain what are these moment. And from there, you can or you cannot, based on the question, you can go ahead and sketch. So that I'll leave it as a practice. You can sketch the shear force, I mean the bending moment diagram, even the shear force you can sketch for this frame. All right. And with that, we can come to the end of that example. When I look at the chat box, oh, my long lost friend, Lokayoj. Lokayoj is a fellow YouTuber, I think from the Philippines. Yeah, I know this is a engineering class, so maybe you might not be able to handle that. But thank you for the patronage. Thank you for the support. Okay, so class, I hope you are together and you've understood what it's all about when we come to the frame. And as I have stated earlier, it's rather easy, only that the matrix may be large. And here we have a few examples you can practice with later on. Remember, when we have a case like this one, a case like this, I'm referring to this, where we have the uniformly distributed load. So remember what we talked of getting the nodal equivalent, load. So you need to get the equivalent piece, the moment, using the fixed head moment, a WL squared over 12, and then you also replace it with the axial load. So you need to utilize that so that now you convert this using the work equivalence method. You convert the UDL to nodal loads, because we said for the finite element analysis, loads are applied at the nodes, quantities are calculated at the node. The rest can be interpreted using the displacement or the interpolating function, the shape functions. So that's the only key thing about this. Once you get this, so you're going to get moment. So this moment now, it means the procedures that we have walked through in the previous slide, or in the previous example, we'll now just have to include the moment. Okay. This example already, the moment is included, and of course we have simplified it by removing that one element, and also the boundary condition have changed because this is Aurora support. Okay, so you can try to work this out, simple case, 2D frame, and see how far you go with. If there is any question, you can always leave in the comment section. But as always, I always encourage people to practice. You do that practice so that now you can be able to really understand where you are stuck. So I'm looking at the chat section and looking whether there is any question, but I know you are digesting that. So as you digest, I would like to show you something else, maybe another method. You might or you might not think or consider it to be maybe an easier way, an easier approach, but well, two options are better than one, so that in case of you find one to be the best for you, then you can always use that. So let me stop sharing this, and then I can share with you a simple example. So I want to share another example. I hope it's this one. Okay. So as I share this, although I'm not going to solve it, I just want to show you another approach that you can be able to use to address how to handle these matrices. So let me know if there is any question or query based on what we have so far looked at today. And I was waiting for this screen to come onto your, I'm monitoring using my phone. And as I said, Zoom streaming, sometimes there's always that lag. So this is an example. This is the one that we went through in, I found it in some literature. But this one is now in empirical unit. The Americans use this unit, but for us, we follow the British standard. So basically, we do not, as much as it's the same approach, we do not use the pounds and the feet, and so on. But I want to show you something. So you're given a frame like this, and then this is a frame, and then you're given the values of E and I and the area, and then you are required to get the displacement and rotation at the two nodes. I mean, we have obtained this matrix, the general case for a plane frame, where we have incorporated the bar element. So this approach, the approach in this book, I hope by now you have known how to make the connectivity, to know how nodes are connected. So you make the connectivity table. So how nodes I and J are connected. Maybe for element 1, node I is 1, node J is 2, like so on and so forth. For element 2, the node I is 3, node J is like this. So Ij. So that now you can be able to make the elemental stiffness matrix at the local coordinate system. Now, what is just doing here in this approach, instead of first transforming to global, so you calculate or you substitute the values, but they are known. So you know EA over L for this element. So you just substitute the values for EA and L. You work out for all the elements. So K prime at the local coordinate system. Then for the same for the stiffness matrix at the local coordinate system for K2 and K3, which are the same. K2 and K3 are the same because you can see the material, we are not considering the orientation because we are just at the local coordinate system. So we just need to substitute the values. So EA, the lengths are the same. So the lengths are the same. So element 1 had a different length. So element 2 and 3 have the same. So you just substitute the values. That's why K2 and K3 are the same. So, and the general transformation matrix, remember this one we came up with where we said for this one represent UI, VI, theta I. And we said rotation does not need transformation, it remains. That's why this remains as 1. So this is the general transformation matrix. So what this approach does, in this approach, you first calculate for the different elemental stiffness matrix at the local coordinate system. Then you use this equation, the equation. So you get, so for the element, first now you because you already know the direction cosines, you come and substitute the values for the different, like for this element, for element 2 and 3, or for element 2 and 3, we have the theta. Look at, be careful about the naming, because the naming is important. This is it will affect the sign convention. This is node 3, so this is the I here. This is node 1, 3. So this is the I, this is the J. This is node 2 and 4. This is the I, and this is the J. This is I. So I believe the author of these in this reference material book did this intentionally, because you can see the way he have labeled the nodes 1, 2, 3, 4. For us, usually the nodes are labeled in a consecutive manner. It's like 1, 2, 3, 4, and you're going to see in abacus that we label them. Usually they go counterclockwise, going upward. Okay. So here he did this intentionally so that element 2 and 3 will be oriented in the same direction, because now these are oriented in the angle. This is 270 or negative 90, because this is the direction for both of them. And then for this one, 1, 2, element 1, of course, the angle theta is equals to 0. Okay. So with that, you can go ahead and he went ahead and calculated what is the element for in cos 90. The beta is 90, so cos 90 is 0, sin 90 is 1. And now from the transformation matrix, he could be able to replace this direction cosines and obtain this as a transformation matrix for the element 2 and 3. And therefore, using this transformation relation, we know the transformation relation is K in the global is equals to T transpose times K in the local coordinate system times T. So doing so for both of 2 and 3, because they are similar orientation and also the geometry and also the material property, he pre-multiplied and was able to obtain what is K2 and what is K3. So you see in this example, of course, he have worked out everything, he has filled in everything, but he started, instead of using the derived stiffness matrix for the beam, he first of all derived for the individual at the elemental scale, then used the transformation matrix. Okay. And then, of course, for the element 1, the local coordinate system is the same as the global coordinate system. So K at the local coordinate system is the same as K at the global. So next stage is to assemble, right? So assembly, we know you assemble, and again, here we have jumped that step, because once you assemble, you're going to have again it will be 4 nodes times 3, so it will be 12 by 12. Yeah. So what we have just assembled here is only for, we have assembled and reduced. We have just assembled those for the reduced or condensed FE equation. That is, we have removed the rows. We have disregarded the rows and the columns associated with 0 displacement. And from our fixity of our structure, we can be able to tell that U3, V3, theta 3, V4, all these are equals to 0. And of course, we have these the known values, 3,000 pounds and so on. Moment were already given us 72,000 pounds pound inch. Okay. So this kind of. So the first thing here, all right, maybe this step we jumped. The first thing that was done is to convert this UDL into a distributed load, equivalent load. Yeah. So to obtain this 72,000, this is just 500 times is WL squared over. Is it WL squared over 12? And then again the nodal force. So this one maybe I need to take you back here. Yeah. Distributed load, we obtain equivalent nodal load using fixed head reactions or fixed head moments. Okay. So you can see how it was replaced. And remember the sign convention from in finite element method is the opposite from what is obtained from the fixed head approach, the principle of work equivalence method. Okay. So that was what was performed first. That's the first procedure. And then next was on now moving ahead and getting the elemental stiffness matrix, then getting the transformation matrix, the direction cosines, and then assembly, disregarding the rows and columns associated with zero displacement, so that we are left with this. So you can see, of course, this is the one associated with non-zero displacement, which was U1, V1, U1, V1. So here, so in your case, I anticipate you, so that it can guide you, I anticipate you to have this U1, V1 in a pencil, theta 1, U2, V2, theta 2. And then, of course, these are the nodal unknowns. This will be the F1 in the X direction, F1 in the Y direction. This will be M1, F2 in the X direction, F2 in the Y direction. This is theta 2. Okay. So with that, we can go ahead and start solving for this equation. Of course, because of these known quantities, like V0, it helps us now to reduce this. This equation can reduce tremendously. So just go ahead and solve. Solving that equation, now you obtain this degree of freedom, the displacement component, inches and radians. And then calculating the reaction force, you go back to this equation. Now, in the other, why I started with the other example, which seems to be a bit longer, is because by just going directly to this reduced equation, you may find like the reaction that you need to calculate, like if you need to calculate what is M3 and M4, they don't appear in this reduced or in this condensed equation, they do not appear. Yeah, because the 3 and 4 are not shown, right? So that's why now we needed to go back and extract this from the elemental stiffness matrix, and then from the slope diffraction equations. So, but here, if you just want to know what is the M3, and M4, so going back to this equation, the equations you need to, yeah, of course, even this one you need to have to know the slope diffraction equation so that you can be able to obtain what is M4 and M3. So I believe by starting with a little bit complex example, not example, detailed, it was not complex, detailed. It was rather slightly detailed so that you can be able to see the steps and where we are coming from. Okay, but after you look at this example and the other one, now you can choose the method which seems simpler to you. Again, the issue of leaving blanks in a matrix, I don't encourage this unless you practice so well, because now you might be feeding those which you are not, you might be feeling. You know, once you have the whole matrix, it might take time, but once you have the whole matrix, you just need to cancel it. But if you start feeling, if you are not very careful with which displacement component are associated, or which degrees of freedom are associated with zero displacement, you might find like you have worked through maybe towards the end, but you ignored the ones that were necessary for the computation or for calculation of the unknown degrees of freedom. But once you practice, then during maybe like in an exam setup, then you can go ahead and simplify your work by eliminating or removing or ignoring those which are associated with zero displacement. Okay. Okay, that's all for that. Again, there was an example. This is the same repeated in your handout there, in your notes. Okay, those are the two examples I wanted you to see. So the second one, I'm not going into detail because it's the same. I just wanted you to see a different concept. Okay. Okay, that's the end. That's all. That's all, and then I welcome questions from you, comments. And I believe today we have time, maybe I can welcome a few people on board so that if anybody have got a live question which you feel you cannot be able to express it very well in typing, then you can join me here. So let me share with the class there. I can welcome a few people on board. Okay, that marks the end of our lesson for today. And I can see you have about 8 minutes. So if there is any one of you with a question, I'm looking at the chat section, it's rather quiet, which means people have understood. I know because you have been having the notes for quite a while now. You have been going through them, you have done practice, and I think that's why there are no questions here. But in case as you do your revision, there is any question, any point that you didn't understand, it's always good to inquire. And I assist you where you are stuck. But I just want to continue emphasizing that practice is the key, because as you look at it, calculations, when they are just projected, solved calculations, they seem just so easy, but when you sit down, let's say, for example, in an exam setup where you are even timed, so if you have not done enough practice, you may find a question which seems so easy, it's taking quite a while to complete. So do your practice. I've been informed by one of the class rep that this semester is short. I had anticipated that it's the normal semester with 16 weeks. So that we have about 12 weeks of learning, then 2 weeks of revision, and then, of course, the last 2 weeks for exam. But now I'm told, in fact, I'm surprised that, is it 19th of this month? You can confirm, Pascal. Is it 19th of this month that you told me the exams are starting? I'm surprised. The semester seems rather short. I know it's because of the elections, but I don't know. It's at a 12-week semester, or 10, 12. So there's just one topic I wanted us to have a dive into. Well, I have kind of mentioned about it because it's about the 2D and 3D finite element, solid continuum. But if you look at it, it's more of emphasizing the theoretical aspect, because when you're doing your practicals, and when we did the tutorial for those who managed to attend, the demonstration that we are doing of tensile testing using steel plate, we are using solid elements. What I realized is that first, yeah, Pascal, you're saying the exam is starting on 25th of this month. So when I look at the timetable, 25th is in 2 weeks' time. So I don't know whether next week should have an exam. It's not an exam. I don't know whether, I'm not quite sure. I'm not quite sure whether next week we should have another class. But anyway, what I wanted to say is that much of the notes that I was to bring forward is what is covered in the Abacus tutorial. I want to talk more about the 2D and 3D element, the issue of the order of element. We have a linear, second order, and so on and so forth. We'll think about it, but even if we don't, I believe as you're doing your practicals, it's good you go through some of these materials in the tutorial documentation, for you to know more, slightly more than what is just covered in class. I know it's an introductory course, but again, as you're doing your practice, as you're doing your practicals, you realize that you are dealing with the solid elements. Solid elements, more or so 3D elements. So it's better, it's advisable to know more of that, not just doing the practicals blindly. Okay. So we shall see. If time allows, we can have one more class next week. If I find like it's too much for you, then you are well prepared. Just do more practice. Even as you prepare, we agree that I'm going to get the practicals, the assignments during the time of exam, and no extension, because now I've already extended. So during the time of exam, I expect to receive everything after the exam, that is. I mean, when we're in the exam venue, once you finish your paper, you should have your work ready. The class rep should have corrected the work so that I can get it the same day. All right, we stop it at that. We have 4 minutes, but I would just like to release you. Thank you for attending this class. I had made it optional, just to see how many of you are interested in this. And I can see the turn-up is quite good. So thank you, that's commendable. Thank you for that. So I wish you well, even as you continue preparing for your exams. Remember, you can always visit these materials, last year's materials. There's a lot of literature and content in this channel, plus other areas that I post. So make sure, or I urge you to utilize those materials, the literature that is available on this course. So thank you very much. I'd like to edit at that. I can see no question in the chat section, so bye-bye for now. Until next week. I'm going to issue a communication next week whether you need to have a class or not. So once I see the timetable, if the timetable says that my paper is on the first week, then no need for exam. But if it's towards the last, then maybe we might need to have just a short, quick one, like a recap. All right, thank you. That's it from me. Bye-bye.